Hello, we're going to take a look at two strings, one stiff and one flexible, and they are designed to be similar to that of a piano string on the C4 note in the piano. The strings are struck by a hammer at 1/8 of their lengths, and I'm going to use a technique by James McDonald from the University of Delaware to solve this problem. However, there are other methods of doing this. Philip Morse presents one in his textbook, Vibration and Sound, and Nicholas Giordano presents one in his book, Computational Methods in Physics. Here's the description of the problem. Here's the flexible string wave equation. Here are the two boundary conditions signifying that the string is held rigidly at the two endpoints. Here are the initial conditions. Initially it's at rest, and it has an initial velocity specified by this f of x function, which is a consequence of the hammer strike. The stiff string is the same thing, except it has an extra term here, making it fourth order, and it has two more boundary conditions down here associated with the fact that it's a hinged connection. Okay, here's a picture of that initial string speed. Here's where the hammer strikes the string, 1/8 of the length. And for example, over here, this initial velocity is 0. Now, to solve this problem, you have to make a Fourier approximation to the initial string speed, which is over here. And here are the coefficients in that approximation. So you could say this is the representation of the initial speed in the frequency domain, and this is the representation of it in the spatial domain. I mention this because you could look at an individual harmonic here and treat it all by itself as an input to the string dynamics machinery. And just follow it through the simulation. Now here, for example, is the picture that we're going to be following. Here are the two representations of the initial string speed in the space domain and in the frequency domain. These are the inputs to the string dynamics model machinery. The outputs are the force on the bridge is a function of time, which is represented by a line spectrum. And then here is the string shape as a function of time, represented by a plot in the time and space domain. These two graphs here we'll show later in more detail. You can also do this, as I mentioned earlier, by just picking one of the coefficients or one of the harmonics in the initial speed approximation. For example, if I pick the 15th, it would be associated with this kind of an initial speed in the spatial domain, which is physically unrealizable, but this would be the relationship. And then you would have a wave shape associated with that initial speed versus time and position. And you could also have a line spectrum of the force on the bridge. Notice that there's one harmonic going in and there's one harmonic or partial coming out. One for the flexible string, one for the stiff string. All right, let's do the simulation. Initially we have a flat string plotting amplitude versus position. Hammer strikes and the pulse is generated and it starts to move to the right. Watch what happens at the reflection. You see that the stiff string is starting to separate from the flexible string. Propagates along here. We have a little underdamped characteristic here for the stiff string. Another reflection. And there's more separation, and we have another little underdamped characteristic here. Another reflection. You can see there's more and more separation between the stiff and the flexible string. And the difference in the two strings is due to the elasticity of the stiff string. And you can go through there and calculate the lead of the stiff string over the flexible string, and I did it for 5 periods. You see here, for example, the red line is the spot in time, moment in time when there's a reflection. Here's the reflection over the bridge, here's a reflection over the right-hand side of the string. The thing to pick out here is that at each reflection there is a step in the lead. For example, we come along here, here's the lead, and then you have a reflection and the lead jumps up to here, have another reflection, the lead jumps up to here. So something happens on those reflections. And it's a whiplash. As you saw when we had the time domain simulation a few moments ago, there's a whiplash effect at each reflection. And this is resulting in an equal and opposite force on the string and on the bridge. And this force on the string causes an acceleration in the stiff string because of its elasticity. There is no acceleration in the flexible string because the flexibleness of the string means it does not respond to the external forces at when that happens to the reflection takes place. Now here is the force on the bridge for the first 15 or so milliseconds of simulation. You can see that the force is proportional to the slope of the string. Over here, for example, is a time versus position picture of the wave shape. You start out with the initial pulse as a consequence of a hammer strike. Actually, you can see right along back here is the initial position of the string, which is flat. Then we get this pulse, and the pulse moves towards the bridge. While it's moving towards the bridge, the slope of the string on the bridge over here, you can see it's still flat. When the pulse reaches the bridge, there's an abrupt change, and now the slope is negative. It's pulling up on the bridge. And this is showing here. There's a spike in the force for both the flexible and stiff strings. And then reflection takes place and you get this whiplash effect. And now you suddenly have a positive slope, which corresponds to pulling down on the bridge, and you get a negative peak here. Then it comes back here and it's relatively flat. You can see that for the blue trace, which is the flexible string, it is relatively flat because there's not many undulations at the bridge during these periods right in here. But there are for the stiff string because these little underdamped characteristics are starting to happen. And you see they start to happen more and more as time progresses. Okay, here's the line spectrum of the force on the bridge. You can see here the fundamental is represented at 261.6 Hertz. The red dotted line is the harmonic position. Both the flexible and the stiff have a representation at that fundamental. Oops. So let's go back here, and you can see that as the frequency gets higher, you start to get a separation. For example, here I think this is the 6th harmonic. The flexible still has a representation at the 6th harmonic, but the stiff has a partial significantly greater than that. There's no representation here at the 8th harmonic because of the position of the hammer strike. What you can see is the frequency gets larger, the frequency of the location of the peak for the stiff string starts to disperse from that of the flexible. There's no representation to speak of here at these harmonics, the 15th, 16th, and 17th, because of the location of the strike. But here, for example, you have a location at the 17th harmonic for the flexible. Here is the 17th partial for the stiff. You see the spacing between the harmonic and this partial is even greater than the fundamental frequency. That's the sound of the flexible string. That's the sound of the stiff. There's no real difference. And that's the sound of the C4 on the Yamaha 120. Okay, we'll repeat this experiment with just one harmonic. Now here we're going to pick just the first harmonic, which is the fundamental. So here's a picture of initial speed if you just picked one of those harmonics. Here it is, for example, only one of the components. And here is the picture in the spatial domain. Here's the simulation. You can see the stiff and the flexible stay right together. And you can also see that there's a smooth progression in the changes of the slope of the string over here at the bridge for both stiff and flexible. Okay, that's one period. There's nothing to show here. Here's a picture of the force. See how smoothly the force changes. And this is because the wave shape changes smoothly. For example, initially the slope is 0, but as soon as that hammer strikes, there's a little bit of slope showing up and a little bit of force. And it's maximum about right in here, and then it gradually and smoothly goes negative. This is over 8 seconds, which is about a little over 2 periods. And this is the picture of the line spectrum of the output, or the force. You see there's only one peak, and it's at the fundamental, 261.6 for both the stiff and the flexible. All right, now let's repeat it with picking one of the harmonics to be the 15th. You can see that the initial speed is physically not realistic. We've got some sort of a magic hammer here which causes the initial speed to be high here, positive, and then negative here, and so forth. So it's not a realistic initial velocity, but it is associated with this harmonic. And we can take a look at the simulation. You'll notice right away they start out together, but then right away they separate and you come out of phase significantly, because there's a lot more activity going on over here in terms of the force on the bridge and at this end, and it's going to cause an acceleration of the stiff string. Okay, we're going to complete 2 periods like we did before. That's no great interest. As you can see here, the force now happens a lot more frequently, but you can also tell even over 1 millisecond the force from the stiff string is starting to lead that of the flexible. And then here's the picture of the wave shape in the time domain and the space domain, and then here's the line spectrum. You can see there is one harmonic input and there's one harmonic output in the force. Here the flexible has a peak at the 15th harmonic, it's right on. Here the stiff has a peak greatly displaced from the harmonic. Its partial is much higher, almost by the amount of the fundamental frequency. So these simulations show that the fundamental component for the flexible and the stiff string behave the same, but the higher harmonics don't because of their greater activity, therefore generating greater force on the bridge and at the other end of the string, therefore causing acceleration such that the stiff string propagates much more quickly than the flexible. Thanks for watching and listening.